Thanks, Dave, and thanks to the sponsors for letting me come up and speak on this one. You'll see you've got some 3D glasses. If people just want to have a look, hopefully that cow will stand out and you feel like you can touch its nose. Later in the talk, I'll be showing you 3D views through here. Unfortunately, I only brought 100 pairs of glasses, and it looks like there's more than 100 people here. I've got a lot of slides to go through. It's hard to try and compress about 30 plus years of history into 40 minutes or so, but I'm going to give it a go. Hopefully you'll find it's an interesting talk. It's all about the regolith. Regolith affectionately sort of known as the crud on top of the rocks. But it's important, particularly up here. This is one of the world districts for regolith, for hideability, as I'll take you through. I just want to make a few acknowledgements. CRC Leem and people like that have done a lot of work, and Ravi Anand, I worked with Ravi quite a bit, and he's been kind enough to let me have some slides. Depth of cover work I was working around here with Placer Dome. Dave mentioned that one. Work around Laverton and also around Kalgoorlie under the management of Mike Christie back in the early 2000s. And I'm going to take you through some of that work, and you'll see some of that coming through. I worked a lot with Nigel Radford, about 20 years or so working with Nige, out of Normandy in particular, and also again with Newmont when I was consulting geochemist with Newmont. And then specialist software with 3D adaptations comes out of a company in America called Microimages, which really helped my career. This is really just a bit of, I say here, I got cow memory fade. I haven't worked a lot in this area in the last 10 years or so, so if I point and go, oh, this is such and such, and I'm wrong, I'm sorry, it's because I've been working quite a few other places around the globe, leading geochemistry and running exploration programs, etc. Most of the areas where the crud is on top of the rocks, as you'll notice, so all the areas in yellows where I've either done regolith mapping or designed geochem programs or been managing exploration. And the other one I've been doing is used to manage remote sensing for Newmont globally, and luckily enough to look at nice images from all around the world. And during that time I also had a research group which allowed me then, the RSRTM group as we set up in Newmont, which gave me money, which allowed me then to be able to do some research, and some of those techniques I'll show you today. It's where the 3D glasses come in. And you're looking at the poor version of the 3D, not the true colour. True colour is beautiful, but I can't do that in the presentation. So regolith, nice simple explanation of it came up by Paul Agnew, who's the chief geochemist of Rio Tinto, and he said basically it's everything between fresh rock and fresh air, which means it's all the weathered rock, plus it's all the crud on top, which is wind-blown, water-washed soils, your alluvium, colluvium, and even glacial deposits, and there are glacial deposits close to here, not far from here at all. And the regolith profile out of CSIRO, this one, you have the two main divisions. You have what we call the saprolith. Hopefully I press the right button and we don't. So you have the regolith profile, two subdivisions. We have what we call the pedolith and the saprolith. In the saprolith, you've got your primary textures and fabrics have been preserved. You can recognise the rock. Colours will change, as you probably know for guys who work in this area. But up in this part here, this is where it's so weathered. You've lost the volume, you've collapsed it. The primary minerals will be there, but the colour and textures and fabrics will go. Quartz veins will break up and collapse down. This is the crud you'll be rab drilling through and wondering what the hell you're looking at when you first come out of uni, and it looks nothing like the rocks you were taught about. All right? But the important thing though in going from fresh rock down here up through this profile is you've released the elements out of the rock. Chemistry's been released, it's made it mobile. And it's most mobile up in this part of the world. The other thing you've done, this part of the section rather, the other thing you've done is you've softened the rock, which makes it amenable then to be eroded out, to be moved, which means then your chemical signature will move. The next one after that, is that whilst this is a complete profile, when you go across an area you're exploring, you can have a truncated profile. You could have transported material on top of fresh rock. You could have that whole profile as being completely buried. So there's a lot of varieties that can happen, and all that then affects your chemistry in particular. And then going down through the profile, there's zones within the profile where elements will be enriched, and sometimes they can be depleted. So particularly in the base of the Jura crust, there's an area particularly where gold will concentrate. And in West Africa and other parts of the world, guys will often, the artisanal miners will dig down beneath the Jura crust, and then they tunnel out underneath, partly because it's softer, but it's also where the gold is reprecipitating and concentrating. That's where nuggets can start to form. So the next takeaway there is really that, you know, elements are being released, and then there'll be zones where they're concentrated within the profile. And so this one here is just showing out of Syro again, just showing how the elements in the upper part of the profile can be concentrated with zones of depletion further down. But then that depletion will end up, sometimes it can be, that it's be concentrated deeper down, and these are the supergene profiles which you get in this part of the world due to chloride-rich groundwaters dissolving gold out and remobilizing down through. And the regolith factor, as I call it, can affect your chemistry. It also affects your mineralogy, and it also affects your geophysics to some degree. And all of these disciplines are key components of mineral exploration. The regolith therefore impacts upon our business. Therefore, it's important that we don't ignore it, and there have been some really significant deposits hidden or concealed by regolith. And I was working in Kalgoorlie back in the late 80s when Kanowna Belle was discovered. You think of Kanowna Belle as only 18 kilometres from here. This is an area that's right next door to Kanowna town site. And there's Kanowna town site. You can read the old books. 7,000 people used to live there. It had umpteen breweries and newspapers and shops and whatever. This is a 6 million ounce deposit as it is now. People walked over it, drove over it, went scavenging wood over it, but didn't find it. Had a single point anomaly on top of it, 360 ppb, with very little dispersion around it. And this is the thing with the regolith. You can be driving over, walking over, you won't recognise it. I gave this talk out at Jundee one time, and we had the chief geologist from Newmont there. And he said, yeah, I was out here, I drove right past Jundee, I was doing uranium exploration. And he didn't see it, because of course you don't see it, it's all covered in red crud. And that's the beauty of the regolith, in terms of still leaving things for us. Now, if it wasn't for the regolith, we'd just employ geophysicists. And we wouldn't be using the chemistry, and we'd just be, except when you're drilling, it would all be down to geophysics. And the reason, of course, that it wasn't discovered, or took a while, it took Delta a lot of efforts and a lot of processes to go through, it's because on top of the deposit, you've got transported overburden. 3 to 4 metres of red-brown sands. It's a dilution on top. And then underneath that, whilst it had been rab drilled, and the trend in the 80s was to just do shallow rab drilling down to 40 metres, wouldn't go down to blade refusal, that was what happened across it. And unfortunately, you've got this pallid, bleached, inferred leached saprolite. Not only is it inferred bleached, it is truly bleached. In the top 30 metres, all the gold's gone. All results less than 10 ppb because of chloride-rich groundwater stripping the gold out. So you still have the mineralised structure passing up through near to surface, but the gold's being leached. Hence you don't get a good strong response on top, and that's why it took so long to discover. There are other deposits, Beasley Creek up near Laverton, right next door to the Paleo channel, 20 plus metres of cover. Lady Bountiful round through there, deposits which are mostly untransported, equivalent of old river channels. Some of them are old river channels, like Moolart Well, that was discovered by Normandy in the late 80s, mined by Regis Mining. It's essentially all transported, and you can go, and I was in Guyana last month, and you can see the analogues to this one. This is Guyana. This is the Arakaka project in Guyana. About 1 million ounces have been taken out of around here just from the surface regolith over the last 90 years. And there's lots of places where these rivers have been mined throughout Suriname, Guyana Shield. And it makes me wonder how many more Moulart Well type deposits are there in this region. I know it's something that Ravi is very keen on and following up on. There's potentially a lot. We know that draining off the super pit there are, and the channels pass out under. Mitre 10 is one of the ones that leads through, to my understanding, and quite a few ounces in that. Other big deposits, Nyankanga in Gator in Tanzania, where I've worked around. 108 ppb soil normally above over 6 million ounce deposit. The reason why it was a relatively low response is you've got a Biff Hills running through, and then this is Biff Scree coming off. There's about up to 60 metres are transported. Where it occurs in the landscape, you've got Lake Victoria off to the side down here. You've got these Biffs. Up on the Biffs, you can get up to 32 grams in some of the rock chips and soils through there. That's Nyankanga down there, and essentially it's been eroding off, putting a cover suite over. I think if this deposit had actually been located about another 100 or 200 metres further to the north, it may still wouldn't have been found yet because of all this transported material on top. Here we are in Burkina Faso, the last project when I was working for Griffin Minerals, head of exploration there, for Steve Parsons and co, the guys who are now doing Bellevue. This is a regolith map of mine, looking at soil geochemistry. It's all about trying to visualise the terrain, and within any area you've got mixtures of fresh outcrop. You can get laterites, you can get thin soil cover, you can get alluvium. You can get flashy soil anomalies. And off to the side there, the big flashy anomaly over there is 600,000 ounces. That was discovered by WMC about 15 years before we discovered this one here, which was 1 million ounces. It's a much more subtle, lower tenor geochemical anomaly, but it's because the regolith is different. This area over here has outcrop on surface, quartz vein that's eroding out. It's going to generate a plume of mineralised fragments, as opposed to here where it's soil cover with unmineralised rocks off to the side, which are then putting a bit of cover over the top, and the chemistry is locked in. So the size of a geochemical anomaly isn't always indicative of the tenor of, or the amount of gold in the deposit. And when we look at the district here, so we can look at this area here in Google Earth, and you know, we've got the Golden Mile, we've got Coolgardie, etc. We can look at it this way, but I'd like to think of it's better to look at the world slightly differently. And so, luckily, we've got satellites. We can look at the world with, this is Landsat. This is data from 2003 with Landsat 5. Today, there's far better data. This is just using what I call DC457. With this already, you can start to pick out where the lake systems are, where the outcrops are running through. There's more changes here in colour, which is related to wind-blown sands. You've got areas of outcrop. These are areas that perhaps soil sampling would be applicable, where you've got some sort of cover coming through and where you've got deep cover. It's about trying to break down the landscape. And if you don't do that, you end up looking at the geophysical image like this, and you think, right, we've got the right structure, and we can trace these structures across, and we come out from the Golden Mile, and we could head up towards Paddington, and you could go and plan a drill program or a soil program or something like that. But realise you've got all this barrier on top. And there's not one technique to discover. We need to change the techniques depending on the landscape. We need to change the spacing of our sampling as well. And there's different ways to help us. So the first thing for me is making a regolith map. And here's my regolith map of the district, which I made back in 2003, just basically breaking out where's the outcrop, where's the colluvium, where's it windblown. And then these days, I'd also integrate it with geology. So we end up with what I call a landform regolith geology map. They're the three controls of the geochemistry. Geology is the source of the chemistry. Landform will give you some indication of what the dispersion patterns are like. And the regolith is whether it's enriched or depleted. And we need to have all of those. And it's nice to have all that on one map. So, just to recap, so sampling the regolith, you're not necessarily testing the bedrock. The regolith type can vary a heck of a lot over a single bedrock unit. The strength and size of geochemical anomalies is that function of bedrock mineralisation, plus or minus regolith, plus or minus geomorph. And regolith's been responsible for hiding some pretty significant deposits. Even in this region, all the big ones still to be found are probably going to have regolith cover over them to some degree. Regolith research, it's been going on for 25, 30 years now. It's come out of necessity. WA has been a prime research spot. And CRC LEAM was one of the big government organisations linking universities and CSIRO and others together to do that. There's a huge repository of information. This website's still maintained. And if people are interested in regolith, then I recommend you go and have a look. In terms of regolith formation, there's lots of factors involved. Geology in terms of how the rocks are going to weather down, geomorph in terms of whether it's going to be preserved, climate, paleoclimate's important, vegetation is important, tectonic history is important as well in terms of uplift and preservation of the material, and human activity has some impact, but minimal. Just put up this picture here as well, just to show you just how much variation can happen in a short distance. You can have everything from bleached inferred saprolite in the foreground, where if you collected a soil sample from here, you may not actually pick up something. Here you've got lateritic material where the chemistry can be enriched. If you go out in the woodland, if you go off into the woodland off to the side, you've got wind-blown sands over the top of laterite. So for your fieldies going out collecting samples, a heck of a lot of stuff that can come back, and then you ship the stuff off to the lab and get an analysis back on it and then have a look. And some people then will take all that and then use a regolith map to try and subdivide their populations down. But what you've got to realise then is just how accurate is your map. If you start breaking out populations and doing subsets on it, can you actually map to that detail? And I say probably not. So in terms of regolith formation, we know that we've got a reasonable handle in terms of gross temperature changes, etc., across Australia, going back well into throughout the Tertiary, back into Cretaceous and further. And essentially, the early part of the Tertiary was warm and humid. This is when deep weathering would take place, particularly Cretaceous and into the Tertiary. It's when your lateritic profile is particularly formed. During the later Eocene, early Oligocene, there was a sharp change in climate, and that's when it goes to cool arid phase. That's when those tropical rainforests would go away and you start getting erosion of profiles happening. And the climate's oscillated, and that's led to periods of deep weathering and then periods of erosion. On top of that as well, you've had continental drift, and Australia moving from being connected to Antarctica, slowly migrating northwards, splitting away from Antarctica, inducing a further sort of climatic change as well as a result, and changes in rainfall. So there have been periods when it's been, this region here has had over 2 metres of rain a year, down to the arid conditions of today. There's also, during this period, there's also been icehouse phases and greenhouse phases, so where the sea level's dropped away and also where it's been very high. How high has it been? Well, some reckon up to 300 metres or more. And within this district, there are a lot of old valleys. There are old marine sediments up around Coolgardie. You can get spiculate beds, definitely marine sediments, to over 280 metres. I've worked out on the highest I've seen spiculate beds or recorded them is 347 metres. And these are races about 15 million years old, which starts changing your thoughts about this area. Hasn't always been the same, hasn't always been desert. We've had tropical rainforests, we've had high sea levels, and therefore then you can then end up, once you strip off the profiles, you'll end up with everything then, I call them constipated terrains. They're just filled up with all the weathering rubbish. It's all just choked up, it can't move. And we then see those remnants today out there in the landscape. We've also had glaciations. And you can see this in So glaciated valleys, there are eskers. There's an esker down near Widjimutha. For those who don't know, an esker is a river that used to be under a glacier. I've been to it. Unfortunately, I couldn't find the photos to put into it. You can go onto it. It's a cobble ridge, and it's a sinuous channel that was under the glacier. You can map using SRTM, shuttle radar data. This is what I've done. You can see the scale there. It's 5 kilometers across. This is out in the Tanami. So we're looking at 30, 40 kilometre long valleys that are up to 5 k's wide. There's one up near Wiluna that's 10 kilometres wide. You map the surface topography, it's dead flat. Those, to me, are part of these old glaciers from the Permian, and before that was the Sturtian glaciation at 525 million years ago. If you go near Lancefield Mine, near Laverton, there's fluvio-glacials on the surface. On top of the granites, you get these big boulders, and people that drilled out there, you can be drilling down through, and what the hell are we getting this rock out? And then you go into another one, and then something else. It's part of old tills that have come in from quite a distance away. So it's a really varied area. Here I've done some regolith mapping, base of depth of cover work across the Laverton region, which I'll come back to, and there was a PhD done out this area. Patrice, I'll think of his name, sorry, I've forgotten his name. This is the current day surface, and this is where I've mapped in the old channels through this region. So Kalgoorlie's down here and Paddington's up here. Topography is quite steep. There's old valleys, there's old systems that you're exploring across. And then remember, this area used to be under tropical rainforest. Hard to imagine. It shows up in the pollen record. 1957, there was a paper written about the pollen record of some sediments out near Coolgardie. It's recording a species called Notophagus, and also extensive palms that were growing in this area about 6 million years ago. So again, sort of change your perspective. And during this time, this is when deep weathering would take place, which is when the rocks are rotting, elements move around, they'll then get concentrated in certain parts of the profile. And then you've got the effect of increasing aridity and a falling water table, hypersaline groundwaters, gold being dissolved as gold chloride complexes, and then as they drop away, the gold gets stripped out of the rock and it can end up going out into the country rock. When I was drilling out, I was involved with the discoveries out at Mount Munga, a company called Mistral Mines in the late 80s. And when we were drilling out there, it was before Charles Butt published his paper in '89. And we were drilling down through and we were into the basalt. We knew the gold was in the quartz sericite schist. And then suddenly these gold values were popping up in the basalt. And you think, what the hell's going on here? And you're trying to model it and it was going flat and the banks wouldn't understand that. You said, well, we've got these flat lying loads, but it just doesn't match the geology. And it's supergene. And it was usually on the interface between the fresh rock and the sap rock, where the water table would sit. So these things are real. I'm sure you've all come across them. And you know, since those days, in the mid to late 80s, there's been a lot of work that's happened. So in '92, this was published by Williamson, and it's about gold dispersion away from the main source. And then there's other elements all move around, so arsenic as well, and copper. And these are good from an exploration point of view because it's magnifying the signal, making your source, your target's easier to find. Orogenic gold tends to be narrow, so we want to have a good dispersion away. So it's a good thing, but it's a matter then of knowing what's what. The other one to think about as well is that over time the landscape's eroding down, it's rotting. The gold deposits didn't form at surface, did they? You know, they form 1 kilometre or 2 kilometres down, but yet we're mining them at surface. So you've weathered away, you've taken all that rock off. So it's worth just considering the effect of that. Apart from anything, you're going to start building up a concentration near surface. And if you've got a metre-wide quartz vein, it's been calculated the rates of denudation, like in West Africa, it's between 3 and 8 metres per million years. Doesn't sound a lot until you start multiplying that over the tertiary. You start thinking 60 million years times 3, that's 180 metres of downwasting. If your quartz vein, say, was 10 grams, for every 100 metres of strike, you actually start liberating, and you do an SG of 2.6 on it. For every 100 metres of strike on a 10-gram vein, over the tertiary at a 3-metre rate of denudation, you actually start putting 468,000 grams of gold, 15,000 ounces into the soil. It's probably some of your prospectors' patches. The other one is sometimes you can go out in the field here, and you'll come across areas where there's quartz all over the surface, and you've probably driven over them. There's quartz everywhere. And you go, well, where's the quartz vein? Where's the source of that? Well, it could have been up there. And you're either in an extensional environment where the quartz veins are horizontal, or a compressive environment, again, give you horizontal quartz veins. And meanwhile, the rock around it's rotted out, and that quartz then just dropped down through the landscape and just ended up on the surface. So if that's carrying gold, that's going to give you a concentration near surface. And that's why sometimes when we can go to West Africa, and it's a rookie thing to do over there, is you go to where the people are digging gold, you go, great, we're onto something here, and BHP did that in a prospect in Burkina Faso. 30,000 people digging gold, there's got to be a lot of gold there, right? Diamond drilled it, concluded there was about 80,000 ounces at the end, and nothing more has been found. And it's no wonder then, you know, sometimes it's not just these prospectors, it's exploration managers end up contemplating their future. And yeah, so work up the prospects a bit first so you don't get too depressed, right? You can generate flashy anomalies, but the source can still be quite narrow. So look for a proper system. There's other mechanisms as well of moving elements around. Vegetation is an important one. There's been news this week about CSIRO and mushrooms and gold and fungi. Frank Reith out of University in Adelaide's been looking at those for a long time. It's all about the way that the plants, some plants in particular, are able to generate cyanide. After all, that's just carbon and nitrogen. Helps to dissolve gold, bring it up through the plants, leaves drop off, and you start building up a soil anomaly. The irony of that was that when I started doing exploration, we used to be told, oh look, don't go under the trees, always go away from the trees, always scrape the surface. You don't want to get any of that, or any of those organics in the bag, because that's bad stuff. Yeah? But we now know that plants can have phytonuggets. There's actual gold inside the plants. Work out of CSIRO. And by mapping the metals, you realise just how clever plants are. Well, I've had boats in the past, and we used to put anti-fouling on boats, which is copper-based. So when I saw this picture here of a leaf, and you see all the coppers loaded on the outside, maybe that's doing the same thing. It's stopping fungi growing on the plant by putting a lot of copper there, which is a poison. And it's taking out, plants are extremely clever, and they can take up metals. And then you've got to think all the time then, that's helping to bring the signal from underneath, which then the leaves drop off and slowly they start accumulating in the soil. So even when you've got a lot of transportive overburden, you can get that signal working through, and some of the work out of CSIRO has done that. So they've got a cherry picker. It wasn't for picking cherries, it was for getting leaves. And they've come up here into the gum tree, and these values here are the values of gold in parts per billion. And this was over 50 metres of overburden. It's up near Rose Dam, so 40 k's north of here, where the mineralisation's through 40 metres of cover. Now the first thing there is, wow, isn't that amazing? 68 ppb is the highest. The other one though, could you use that then as a sampling technique? And the answer to that is probably not, because look at the insight variability. You're going from everything from 1 ppb to 68. So unfortunately you could be sampling the wrong part of the tree. But then think what happens to those leaves over the years. They drop off. And then underneath there then is that great accumulator, the soil underneath that. So what a great way then, that's building up the signal, the picture through it. And then this one here, Phyto section, this is what the trees were going down through. So again, CRC Lean, great repository of all this information, well worth a look. And realise the value. The other one then is realising as well the role of calcrete. People do calcrete sampling. This work, a colleague of mine, Mel Linton, I'm working with on the XRF gold technique, detector, who invented detector as well. He worked out that working around Mount Hope, so this is going from surface down to 2.5 metres, 2 metres, and then this is showing you gold concentration, and then these are your calcrete concentrations down through the profile. So within these nodules here, this is where the gold's accumulating. The theory on that one is that it's actually what's happening is that the trees are growing down through this lot. Plants then bring the gold up to the surface, the leaves drop off, the gold's transported in organic acids, It then hits this base. Oops. It then hits the calcrete, which then is a base, so then the gold precipitates out and it's co-precipitated on the calcrete. And that's the mechanism by which you start building up a signal over time through the calcrete. So calcrete in the right environment makes a great sample media. Use an auger rig to go down through it and to sample that. And then out of that, out of this work, it's all about trying to take a primary source, look for the concentration, and then work out. Sometimes you're going to need to use an auger rig, sometimes it could be on surface, but just realise that the signal will get broader depending on where you are. But unfortunately, other times is you can have fresh rock with just transported material on top, over the top of that. So a lot of variety. So going around the area, you can get residual laterite. You can call this one residual because you can see the quartz vein there. The rock's weathered down, forming a laterite. You can have these breakaway zones like this, and you can drive up them. But unfortunately, not all of them are residual. And this one here is what I call a ferrocrete. It's transported, it's part of the old river valley. And that's where you get these piezolyths with these concentric rings around them, where they've grown. These things have been dated. Not this one here, this is sitting in my office at the moment. But some of them have been dated, anything up to 60 million years old for the core of a piezolyth. The next bit then, 20 million, and the outer core down to 5 million. Chance of that one piezolyth staying in the one area for 60 million years, I'd say, is pretty slim, which then has implications. These things will trap gold, scavenge gold, and other metals. Something for another story. This out of Black Flag, and you can come across these ferruginous type deposits like this. First question I want to know is that residual transported? Go and have a look. Went and had a look, and you go, okay. Down here, I don't know if this zooms in, I don't think it does. The bottom of this one, there's river gravels. So it's part of a ferrocrete, it's transported. Plateau like this is on the road to Ora Banda. So what I do on these ones here is go and have a look. Go up the top and have a look. And when I get up the top and have a look, I find that there's a rubble, piezolytic gravels. This is part of an old river channel. Has implications in terms of people that do lag sampling. I don't know whether people do lag sampling now, but lag samples, scavenging metals, but if you're dealing with an old river channel, then your lags could have come from kilometres away. And after all, piezolyths just get transported. They're just like any other bed load. Get transported down the rivers and out. Travelling around a bit more around this region, just showing you, I suppose, the variety of regolith around the area. Here's one, I think it's out near Black Flag, typical woodland. And here we've got saprolite almost to surface, typical calcareous soils for this part of the world, and then with the trees on top. Sort of area I'd say is fine for soil sampling. Keep going around the region. Look at an area like this. How would you work out whether or not we could soil sample this? Should we be augering? Should we be drilling? How would we explore an area like this? So what I do first up is I go out and drive around and have a look. Here I'm standing on a dam wall, so it's easy to have a look. But in this area sometimes, just the fact we've got sparse woodland tells me it's probably pretty shallow. Saprolite pretty close to surface. Radiometrics can be a clue. Sometimes just the geomorphology, the topography can be a clue as well. But before we start doing an exploration program, I'd want to come out and check over the landscape and have a look through. And then it's very much a case of being opportunistic. So here in the foreground now, you can see I'm standing on a dam. There's a lot of saprolite here. This is essentially all extremely shallow cover over sediments. Here now, this is one of the other pits in the region, and unfortunately, sorry, I've forgotten which one it is. Extensive red-brown soils. There's a darker horizon within this one here, and I think the next photo is a zoom in on it. Now you can see that we're going from red-brown soil, piezolytic, or more sort of iron granules. Deep in the profile, it has to be transported. So thick transported. Other times in this area, this on the road to Mount Pleasant. It's like, what's under my feet? How deep's the cover? Got no idea. So at this stage, there are actually ways you can get some sort of indication. So one of the things to do is actually look at the lag. The lag, for those who don't know, is all this coarser material that's lying on the surface. And when you have a look at this one here, this is the lag from this site here. And what was interesting when I started looking at this one is look how rounded some of these fragments are. So that would probably be transported, and luckily there was a drill hole nearby and it showed there's about 80 metres of cover. But here's another little tip, I suppose, is that when you're out there, once you do have cover, take it as if you didn't have that drill hole. And how could you tell that there's cover here? How can you identify that before you put the hole down? And what I normally do when I'm doing regolith training, I do quite a lot of that, is you tell the geos, hey look, don't tell everyone, but have a guess of what you think the cover suite might be, or what sort of rock's underneath here. And sometimes it can be the type of tree, it can be the type of lag on the surface, it could be the soil colour, it could be the soil texture. Sometimes you've got termite mounds and you get material on those. And have a prediction of what you think is under your feet here. And that way then you can start to train your eyes and start to make predictions. And then that improves your exploration, your ability to explore an area. It's all about self-training. People can't come in and teach you this stuff, but they can teach you to open your eyes to what's there. And slowly you can start to pick up these things. So, yep, boss, it is funny, there is a drill hole nearby. You can be very smart afterwards. You can actually do some forward predictions as well. All right, another one here. This is now up near cane grass swamp. So we're heading north up towards Goongarrie, up the highway towards Menzies. Wind-blown sand, a lot of sand dunes through the region. Sand dunes were particularly building up during the last glaciation, peaked about 25,000 years ago, sea level about 100 metres lower than present day. For those of you who live in Perth or ever go scuba diving, you've got to think, right, Rottnest trip. You could have walked out to Rottnest. Scuba diving off that area, as I used to do when I lived here in Kalgoorlie, or down at Esperance, going down to Esperance and scuba diving before the big whites, great whites showed up. In the same numbers, or seem to show up in the same numbers, is that you drop the sea level, suddenly then you've exposed all that sand at a time when the climatic zones are being compressed, which is when the winds pick up. And what happens then? It got picked up and dumped inland. Major diluting in the soils. A lot of dunes around, probably, and a lot of them attributed to the Devensing glaciation period, 25,000 to 10,000 years ago. And underneath these, when I looked under this one here in this car park up near Cane Grass Swamp, you go, oh, hang on, whoa, we've got double trouble here because we've also got lots of really well-rounded little pebbles in there. What are those doing under there? So not only have we got something with low cation exchange capacity that won't hang on to elements, but we've also got transported overburden underneath it. So if I had my main geology unit passing through there, not going to use surface sample, I need to ring up Raglan drilling and get some bags from Western X and something from Reflex, and then get out there and use all that to help explore. Another one then, Spinifex Woodlands. Now is that over granite or is it over wind-blown sands? Depends. Radiometrics will help you on that. Calcretes we've gone through. Now you can look at this one here again. What the hell is under our feet here? Well, luckily this one here I can turn the other direction and I can see there's an old deep lead Paleo channel. But then look at the lags and try and work out. Is there another way? Is there something else in the geophysics? Is there something in radiometrics? Is there something in EM data that helps tell me what's out there? And don't just look at it, try and map it. Because when you map, it forces you to understand the data sets. Everyone can look at a picture and think they understand it, but you try drawing lines and have it so that someone else, your boss, can pick it up and put it on a tablet these days and go out in the field and drive around. People get nervous about it then, but honestly that's the best way to operate. Don't just work with mental maps in your mind. So regolith mapping started here in Kalgoorlie. It was one of the first places. First published map was here in Cal. Lots of different mapping schemes came up. CSIRO, GSWA, AGSO, Geochemics, a consulting company in the 80s, and then Regolex, my company, and I have the FRED scheme Red came out of CSIRO. I didn't like that because not all laterites are residual. I have Fred to cover it. Ferruginous regime, residual erosional depositional. It's all about trying to understand your landscape. We map the geomorphology because the geomorph is controlled by geology. In a regolith-dominated terrain, you don't always see the geology, but you can see the geomorph, which then will give you an insight into it. It's all about physical dispersion. Regolith gives you the chemical environment, and then these days, as I said, I combine geology with it. And I think a correctly structured regolith map is one where it's possible to visualize the terrain. You can understand, you can look at the map and you go, oh yeah, gee, I understand what that is. You don't want to just have it with a series of codes and you have to go from code to legend and back and forth. Have it in your face, see it. And then you can then work out what sampling technique to use, what thresholds to apply to your surface geochemistry. It can't be an academic process. We don't want to start, we need to lump stuff together. We don't want to split everything down to the nth degree. It's got to be, we're an industry. We need to map relevant features. If I took too long doing it, I wouldn't still have a job. I've been doing this for 25 plus years, so it must be going all right. We're covering large areas, so have to have a high reliance on remote sensing. And it really helps to understand the landscape evolution process. So normally what I say is you've got to look in 3D, think in 4D, with 4D being time. And it's about having that landscape history so you can predict where the problems are. And regolith map, ideally produce them at the start of the exploration program. You can then work out, you can review any historical data, you can plan your orientation surveys, you can select your right geochem sampling technique. It'll help you with geological mapping in terms of picking out where outcrops are likely to occur, helps you with your remote sensing interp, and also help you with your error mag checking, because where those structures are running through, you know where they are in erosional terrain. Don't go chasing features out in deep depositional transported cover. So help on that. Often though, they're produced near the end of a program, which I used to call them the fire brigade jobs. When I was working for Normandy and Newmont, it's like we spent tens of millions of dollars. Do we drop the project or don't we? Oh, let's go back to basics. Let's do a regolith map first. Let's review all the geochemistry. Useful exercise. Sometimes then you go, hang on, why do you sample soils at 10 by 10 metre grid? If you take out every ninth line and every ninth sample along lines, i.e. you've taken it down to 100 by 100 metre spacings or something like that, you've still got the same answer, you drill it here. And believe me, I've seen grids like that over the years. People like spending budgets. And then basically we just divide it out into regimes, landforms and culture. This is for areas with bad topo maps, so you need to know how to navigate around. As I say, I have the Fred scheme, ferruginous regime, which is iron-rich regolith. We're dealing with residual, which is where it's soil cover. We're dealing with erosional, which is where it's outcrop, out or close to surface, where soils would be reliable. Then you have various depositional, which could be alluvium, colluvium, glacial, windblown type materials. Lacustrine. In the tropics, if you're dealing with dense tropical rainforests, like where I was last month in Suriname and Guyana, basically it's really hard to tell whether it's iron-rich or outcrop underneath the canopy. There are ways of doing it, but it's not easy. But it's good just to map out the landform in that situation. When I was doing the mapping around here, this is my office in West Perth, which looks, I was there this morning, looks remarkably similar. Still, apart from the stereoscope's gone, back along I used to use air photos a lot, and that's because you need to look in 3D. But there's lots of problems using air photos, like they're not ortho-rectified, which means you have to twist it, and the plane was hitting an air pocket, or the pilots were talking to each other and tilting it sideways, and so you got changes in scale and because of the pitch and yaw of the plane. So you have to ortho-rectify afterwards. It's really time-consuming, but it worked. And then when I was doing that, I used to have a laptop. I thought this was really cool at the time. I had the laptop off to the side, and I'd look through the stereoscope and glance at the laptop, and this is out near Black Flag, I think, on screen at the time, and I could go back and forth between that. These days, I have a true colour 3D monitor. I have 3D glasses. Shutter glasses, I can turn on the geochemistry in true colour, I can turn on radiometrics true colour. magnetics. Everything stands up in 3D. It's all auto-rectify. I can then draw on screen. I can do everything. It works beautifully. And I've had this since 2009 when I developed it within Newmont. Luckily, it wasn't kept in Newmont. And it's just transformed the way that you can look at anywhere. I can look at anywhere in the world in 3D. On my laptop here is the whole world, the elevation model at either 90 metre or 30 metre for the whole world. So just click on it, goes in 3D. About this time, if you haven't opened up your 3D glasses, it's worth opening them up. Because then you can look at this one here just to check and see. Not everyone's eyes are going to be able to adjust. Men in particular, if you're red-green colourblind, you won't find this one right, but hopefully you're getting that wow factor now. And that cow, you feel like you can touch its nose and it's all soft, and if you move your head, then its ears are going to move from side to side and things like that. And that's the power of 3D. And sorry I didn't bring enough glasses, I brought 100. Hopefully people can share around. It makes things feel real. Now, any pictures now that have a picture of 3D glasses, it needs 3D glasses. So we can look at this area here, and there's the elevation model. Oh yeah, pretty dull. And I can do standard exaggeration on it. This is once time, it's pretty dull. So what I do is I actually put 25 times vertical, because we're in such a flat part of the world. This still won't be in 3D. This is just standard, no glasses needed on this. So just by crank up the vertical exaggeration 25 times, it's starting to look a bit better. Now what I've done is I put this into 3D, which for me is just a click of the button. For those, we were experimenting earlier. Hopefully for some of you that's starting to stand up and it's starting to feel a bit more real. So just to put you in perspective where you are, this is the super pits here, Kalgoorlie. This is Paddington. Up through here, which means Bardock. Bardock would be up here, Ora Banda out here, Kundana through there. So we're looking at a reasonably large area, and I think now I'm just going to zoom in. And this is now Lady Bountiful and through that area. Even if you don't have the glasses, hopefully now what I've done is I've just put a vertical exaggeration on it, and those ripples are essentially 1 metre contours in the image. And with the glasses means you're starting to see some geology. If you know about flat irons and how they indicate dip, you can see those in 3D. But the other one hopefully you can start to see is you can see alluvial fans. So through here, coming through there, that's a depositional zone. You can see where it's eroded off from. Out through here, this is Paddington. So broad arrows about here. Yeah? And you drive over that, you can't see any of that. Yeah? It's the power of using elevation models looking in 3D. So then if you start putting your chemistry over the top of that, then you'll start to see where the chemistry will be, what I call it's turned on. It's connected to the rock, and then you'll see where the signal will turn off. And where you need to be changing your techniques. Oops. So here is the chemistry. I've got 70,000 soils through here. It doesn't work fully, and it won't work properly with these glasses. You need to have true 3D glasses to do that. But then you're starting to build, exploration is all about building a jigsaw puzzle and recognising which pieces are in the right places, which ones to believe, where to look for high values, which will be out in erosional zones. And I did this afternoon. I put this together after I met Alicia earlier today. Between 3 and 4 o'clock this afternoon I did this one, so I haven't had time to look at it. But already to me there's some standout areas, like this little blip down here. It's low level, but hey look, it's standing out as something significant to me. There's a whole stack of things through here, subtle anomalies that become significant. Maybe it's where the elements have come up through the trees. But when you start looking at the landscape the right way, you can start doing that and building the exploration jigsaw puzzle. You then bring in good geology on top of that. And then you know which way to chase. This is now 3D. just to show you an even bigger picture, here's the scale down the bottom. That's 10 kilometres. This is Norseman, that's the Jimbalana Dyke. Princess Royal would be in here. I've forgotten the name of the lake, someone tell me. One of the lakes, and then Cowan. Yep, Lake Cowan. That's Lake Cowan, so we're heading up towards Kambalda and up the way. But the nice one is you can do this anywhere in the world, and I've got a quiz at the very last one. You have to tell me where it is, and I'll buy you a beer at the end. All right, so that's the end of the 3D glasses. So remote sensing, we use imagery, digital elevation models. There's been some really significant changes in the way we can do that in the last decade. It's all about resolution and bit depth, etc. And it's great. Luckily, Donald Trump doesn't know yet that the US, I should take that away in case you watch the video, that the US taxpayer and the European taxpayers give away a lot of free data. So Sentinel imagery, Landsat imagery, brilliant. When I was doing the mapping before, that Landsat image was $3,000 US. Now I can download last week's image for free. Sentinel imagery, which is 10-metre resolution, courtesy of the European taxpayer. Last week's image, free, 10-metre resolution. It's fantastic. And then there's great software now, even with QGIS and other software programs to be able to process it. So really, really big changes, plus the ability to go out in the field and navigate around with this stuff. I load onto a Samsung Tab A tablet, $180 worth Aussie Explorer GPS software, and you can drive around and track yourself for less than $220. Cheaper than the GPS, you can have a PDA with everything loaded on it. So it's great. The other one, as I mentioned, is resolution. So, you know, SRT M1, 30 metre through to 1 metre, 10 metre, 30 metre through to 1 metre elevation. This is shot from 770 kilometres up, 15 centimetre vertical accuracy through Photosat in Vancouver using Digital Globe's WorldView 2 satellite, or WorldView series of satellite. And with that then, it's easy now to make regolith maps. And then this is just another example from this region added in this afternoon. It's all about the elevation. You can see, look at this, you can see how that's Kundana there. And you can see then how it's eroded out, and you've got these alluvial fans coming off. You drive over that, you won't recognise it. Put a good vertical exaggeration on it, process the elevation model the right way, you can pick out the difference between residual and transported. Very clearly, here's where I did my initial regolith mapping from air photographs, and I just highlight here. I've made a mistake, I should have a line going through there. But because I switched to a different data set, of course, I did correct my mapping for the final hand-coloured version before I converted it to a GIS product. So powerful stuff. This I was doing back in 2003. These days we do a lot more. Radiometrics. How many people use, I won't ask you, too many hands. Radiometrics. Ternary radiometrics, fantastic data set. This is near Paddington. How on earth can you interpret that? Well, the first thing I do is put an elevation model behind it. Suddenly you bring it to life. And then I put in the regolith interp. This is my air photo interp that's been ortho-rectified. And now suddenly then, exactly the same area, with that cruddy radiometrics, I can now see where the outcrops are. I'm mapping out where the roads are, I'm mapping out the drainage, I'm mapping out erosional zones. So through here I could come and collect a stream sediment. If I want to check this area, one sample, a decent high quality stream sediment, we check all that area. I'd do another stream sediment here if I was coming through here for the first time. We've got a drainage going off that way. I wouldn't do a stream sediment up there, because out through here we've got soil cover, not cutting into the bedrock. I'd need to change my techniques through here and do soils instead, or auger it, or ring Raglan and get them to drill it instead. Geophysics. Here's some geophys with basic geophys with being processed with high frequency. High frequency is picking out where the piezolis are within the data, and with that then it's giving extra noise, and that's showing depth of cover. So within the geophysics you'll get features. Here we've got paleo channels, showing up in geophysics, and people might have seen that. Maghemite-rich rims, kilometre or two wide. I'm mindful of the time. EM data. This is near Laverton. Super saline waters, so we're ending up with highly conductive areas. These numbers here are showing depth of cover, and the EM data clearly showing that. So here's my regolith map across the district. If you zoom in now with the GIS product, like I said, it's all about being able to visualize the terrain. So here I put an elevation model behind it. Blue is erosional areas. So that's where outcrop is out or close to surface, where I could soil sample and stream sediments with confidence. I'd expect it to be easy to find. What I do then is greens are depositional. These are depositional, that's alluvium. Reds here are mines, as they were. Now what I've done is I brought in geology. I drilled this one out I was out here in January 1986. And that's Blue Funnel. We did the first drilling on that with Naranda, Australia. And I do have the drill database through here, 438,000 drill holes. And I wanted to load it up because one of the ones that interested me is that when I brought that in the other day when I was preparing the talks, I found that all the drilling actually stopped right there at the pit. It doesn't actually continue through here, even though you've got the main stratigraphy running on through there. And you have to wonder whether, if it was following up on soil samples, whether or not, because the soils aren't going to respond because you're out and transported, is there more to be found? Well, I went on to Google Earth last night and there is drilling out there now. But it's just one of those things that when you look at the data the right way, you can start making those, you can start knowing when to follow up and when to do more work and which techniques to do. In this region, another thing I've done apart from the regolith mapping is depth of cover work, which I did around Laverton, 2004. It was done as part of a consortium, so it was shared between Placer, Anglo Gold, Metex, and one other company. And they pulled all their data, they gave me all their drilling data, and I just say there that by collaborating, and Greg Hall, people know Greg Hall, puts this one up as an example of the great value of sharing data. 1 + 1 is greater than 2. Two companies come together, you get a multiplier from it. It's a problem in our industry that people are very cagey about sharing data and information. What you've got to realise sometimes is we're actually in competition against banks and telcos. If we're not making discoveries, the funds will go to other industries. And we would do far better to collaborate more. One reason I don't work for a Newmont any longer or some of these other companies is the stuff I was doing back then I couldn't talk about. There's no way in the world I'd be allowed to stand up at a conference like this or come and talk at something like this to industry about what I was doing, what I'm doing, 3D monitors and things like that, because they don't want to give anyone else a break. Right? But we're actually better off by sharing information because otherwise the funds will go to cannabis. It'll go to cannabis. The Canadian market's killed. It goes up in smoke, yeah? It goes somewhere else. So just share a bit more. So out through Laverton, you know, all the early discoveries are out in the erosional zone. So we're looking down here, a glary image, and you've got Laverton in here, you're looking down through, there's Granny Smith. Down the way, we're looking down Lake Carey. You've got erosional areas. This is where the early discoveries were made, out through here. You've got depositional zones. We know there's cover, you've got a salt lake, but then the big discoveries are all out under the cover. So Sunrise Dam, 14 ppb soil anomaly on top of it, for plus 9 million ounces. Right up against the edge of it goes up to 140 metres of cover once you get out just off to the edge of Sunrise, out to, you're about there, you're into 140 metres of cover. Wallaby, under 60, 70 metres of cover. No surface response, it was a geophysical discovery. So what I did, we pulled the data, I did a surface regolith map through the area, there's this current surface DEM. I did a regolith map first, and then I took all the drill data. By pooling from 4 different companies, we ended up with 38,000 drill holes with depth of cover, and I manually contoured them. And with that then I was able to produce an elevation model, isolines. I was sitting at the traffic lights in West Perth driving home and thought, well, hang on, how do I convert those lines and make them look a bit more specky so that people could see that and fully appreciate it? I had the aha moment, went, how about I merge it with the surface elevation model? So that's what I did, and I ended up producing this one here, which I call a pseudo-paleo topography. And this is bottomed out at 90 metres, but essentially what you've got here, this is where sunrise is. You've got Mount Weld with the carbonatite in here, but the drilling's mapping out and picking out these dendritic drainage patterns. Areas that are currently flat, you can pick out the old channels. The useful thing about that then is if you drill down through cover and you've got anomalies in the cover, instead of doing a grid pattern around it, you can start using it like drill rig, like a stream sediment sampling technique, and work your way back up the old topography, back up the old drainage system. Apart from it, and yeah, as I say, luckily we had lots of data, so they've been drilling out on the lake at that stage. Cover looks like this, but you know, the drilling was showing up to 90 metres of cover under here and then back out into the outcrop, part of this old glaciated terrain. So extracted out 34,000 drill holes, pulled out the different materials, used the geophysics, used things like the edge of the old rims, used EM data, and then hand contoured. And then merged that, created that into a DTM and fused that with the surface data. Before doing that, I used a digital raster paintbrush and backfilled all the pits and took out all the waste dumps and everything else before merging it, and took out all the sand dunes on the lake. So you end up with a smooth one. And with this then, you've got some indications now. This is taking the regolith mapping to another stage, another level. And with this then, you've got an idea of, is there a chance that the chemistry could be working its way up through cover? Or whether there's no chance at all, and also have a sense of budgeting as well. And so it ends up looking like that across the area. And sunrise comes out like this, and what they did, and this was all under confidentiality until luckily someone from Sunrise ended up, or Anglo Gold put it out as a poster at a conference. And went, you beauty, they've taken my mapping, and this is showing where they've traced the gold coming down the old Paleo channel at the base of where I've mapped it, which is just like those rivers in South America now. So again, I wonder how many more places are like this around this region. So I've done the same thing here in Kalgoorlie, which I did back in 2004. In that case, there was 138,000 drill holes with Bolster transported, of which about 98,000 gave me confidence that we could use those. Unfortunately, it was only a 30-day job to work through. It was a short-term contract, 6,000 square Ks. A complicated area. I'd already finished the regolith mapping at that stage, worked its way through. Around Mount Lady Bountiful, there were 30,000 holes. It was all very easy, not a problem at all. So easy to come through and map that. But ultimately went through and produced this depth of cover map. And unfortunately, I couldn't find it when I was preparing this talk. So otherwise, I was going to make it fairly specky. And it's been used for things like budgeting how many meters you're going to need for drilling, check the effectiveness of the surface work, whether all anomalies are identified, and also work out the hideability. So the regolith factor, it's real and significant, can't ignore it. Most of the remaining near-surface mineral deposits are likely to be obscured by the regolith. I just bring in this picture here from a recent ASX announcement. It shows a multi-phase drill program, and their exploration technique is using drilling. Great for companies, 2.5 kilometre spaced drill traverses, multi-year program, covering tens of kilometres of strike. All I'd say with that is, how high risk is that? How high risk? And is there a better way? For those companies that are just, and this is where I've already promoted Raglan, drilling is great, but not the only tool in the exploration arsenal. There's other techniques we can be using. I know of some companies that just rely on drilling. But don't forget about the basics. There's soils, there's augurs, there's stream sediments, there's lag sampling. It'll all work well as long as you understand the regolith. And for the drilling companies, they'll make far, far more money from drilling out a resource and doing drill and blast in the mine afterwards, and doing the deep directional drilling afterwards as well. So frankly, I would save the drilling, dollars back, use fit-for-purpose geochemistry, use regolith terrain, use the data sets, courtesy of the US taxpayer and Europeans and others. Build the jigsaw puzzle and work your way through. And that way then you can find the wealth that people have been driving over, walking over for decades. And so yeah, recognise there's a problem in the first place, understand the regolith, actively incorporate that into your exploration program. So lots of new tools, look in 2D, preferably look in 3D, thinking 4D. And with that, you've got a good chance of making discoveries. Manage the Regolith Factor, otherwise it's going to be the next generation of explorers who will make profit from errors, avoidable errors, and some people are already on the learning curve. So thank you.